Okay. Let's go ahead and get started here. I'm going to erase something. Boom. So this next section is about chemical equations and chemical analysis. It's a kind of long section and you need to see a lot of examples. So this is going to be divided into two lectures. And the first, we do some examples and we do some explaining about the principles. And the second lecture will be largely just doing problems for you to look at and see how they are solved. Okay, so chemical equations and chemical analysis is using stoichiometry principles to analyze a mixture of compounds, but it's also used to find the empirical formula of an unknown compound using stoichiometry. So here we're looking at two different things: analyze a mixture, analyze a pure substance. So I've detailed them a little bit more here. So the two major types are the analysis of a mixture. For a solid, you're going to determine the mass percent of a substance in that solid. This is very important because if you are digging up dirt and you're looking for iron in that dirt, you want to have a larger mass percent iron in the dirt so that you can get more money out of that shovel full of dirt. For liquid, you want to determine the concentration of a dissolved solute in the solution. So remember, a solution is comprised of a solute and a solvent. You know, you learned that way back when in your previous chemistry class. So here, we're trying to determine the concentration of that dissolved solute. And we'll learn about concentration in this chapter also. We'll see examples of this. This gets its own little section, as it were. And we're going to do quantitative analysis of a pure substance. And here you're trying to determine the formula, empirical and perhaps molecular, of a compound and perhaps its identity. So let's look at quantitative analysis of a mixture for a solid. First, you need a known chemical reaction for the substance of interest in the mixture. The substance must react completely and quantitatively. So when we say quantitatively, it means you must be able to measure something about the products that can be used to determine the amount of substance in the mixture. And usually determine the mass percent of the substance in the mixture. And when determining mass percent, this is the general idea of percent. Percent is part over whole times 100%, where part is the substance of interest in the whole, and the whole is the part plus other stuff in the mixture. So this formula can be used for anything when we talk about percent. Specifically for this case, when we talk about mass percent, it's the mass of the substance in the mixture divided by the mass of the mixture times 100%. So here, how do we get the mass of the mixture? Well, usually when we're doing this analysis, we just have a sample of the mixture. So mixture, sample, same thing. So you take your sample and you weigh it. That's the mass of the mixture. How do you get the mass of the substance? You have to do a chemical reaction. So here's an example of an analysis of a mixture. Sodium sulfate, Na2SO4, occurs naturally as the mineral, thiahardite. To analyze an impure mineral sample for the quantity of sodium sulfate, the sample is crushed, then dissolved in water to form a solution of sodium sulfate. Now, the reason this forms a solution is because sodium in ionic compounds makes the ionic compound soluble. Next, the aqueous solution is treated with aqueous barium chloride to give solid barium sulfate. So here you have your dissolved sodium sulfate from your thiahardite, and you react it with barium chloride. And in the reaction, you get this solid, and you also get this aqueous sodium chloride. Now, you can filter this mixture through a filter paper and collect the barium sulfate. And, you know, I'm not describing the exact technique, but essentially you can get the barium sulfate isolated on a filter paper, let that filter paper dry, and you can weigh that filter paper before and after, and the difference will be the mass of your barium sulfate. So they're saying suppose a 0.498 gram sample of, oh, it's thenardite, not thehardite. Thenardite produces 0.541 grams of solid barium sulfate. What is the mass percent of sodium sulfate in the sample? So here's the solution written out at first. We need the mass percent sodium sulfate, which is the part over the whole times 100%. In this specific case, it's going to be the mass of sodium sulfate in the sample over the mass of the sample times 100%, where the sample is the mixture. So we need the mass of sodium sulfate in the sample. We have the mass of the sample. It's 0.948 grams. It's given right here, the mass of the sample. And so we already have this bottom part right here. Now, to get the mass of the sodium sulfate, we're just going to use some stoichiometry. We're going to start with the mass of barium sulfate formed, turn that into moles of barium sulfate, that into moles of sodium sulfate, and that into grams of sodium sulfate. So here's the mapped out strategy. Start with the grams of barium sulfate, turn that into moles of barium sulfate, turn that into moles of sodium sulfate, and turn that into grams of sodium sulfate. Here, we're going to need the molar mass of barium sulfate. Here, we need the coefficients of the balanced equation. And here, we need the molar mass of sodium sulfate. So I've determined the molar masses of sodium sulfate and barium sulfate and have written them here. Okay, so let's see what the solution looks like. So the mass of sodium sulfate in the sample. Now here is my guide, if you will. I'm going to start off with 0.541 grams of barium sulfate. That was given by the problem. I'm going to multiply by 1 mole of barium sulfate per 233.40 grams of barium sulfate. Now, you've seen me do problems before if you're watching the lectures, and you know that I'm going to put the identity of the substance in here. We call those labels. And then I'm going to multiply according to the balanced reactions. Let me pull the balanced reaction up. So here's the balanced reaction right here. We're going to say that there's 1 mole of barium sulfate to 1 mole of sodium sulfate. So I'm going to put 1 mole of barium sulfate here and 1 mole of sodium sulfate here. Now I put the mole of barium sulfate on the bottom so it would cancel with the mole of barium sulfate on the top. Okay, and then finally, we need the molar mass of sodium sulfate, and we're going to put 142.05 grams of sodium sulfate on the top. And we're going to put 1 mole of sodium sulfate on the bottom. And since this cancels, and since this cancels, we're going to be left with grams of sodium sulfate. And you know me, I like to estimate, so I'm going to go ahead and estimate here. This is half. Half of 142 is 70. 70 over 233 is roughly 70 over 210, which makes it 1/3. Okay, so the answer should be around 0.3. All right, well, let's take a look and see what we get. So 0.541 times 142.05 divided by 233.40, and we get 0.03293. I'm carrying an extra digit along because I know this isn't the end of the problem. Okay, now to calculate the mass percent of sodium sulfate, we're going to use that 0.0329. Actually, I made a mistake here. and I put an extra 0 in, I'm going to cross that out and put 0.3293 grams. Okay, I'm looking at my calculator and see I put a little extra 0 in there. So I'm going to cross this out also. 0.3293 grams of sodium sulfate over the whole, which is 0.4, and I have to look this up in the problem, 0.498 grams. And then we multiply by 100%. Okay, and essentially these units go away, as it were. If I wanted to, I could leave labels in here. Put my little arrow there. Grams of sodium sulfate per 0.498 grams of mixture times 100%. And let's see how these look differently when we finally solve the problem. So I'm going to divide by 0.498, multiply by 100, and we get 66.1%. Now with these labels in here, what we would get is 66.1% sodium sulfate mixture. And what this means is you have 66.1 grams of sodium sulfate per 100 grams of mixture. The percent is that right there. So percent means 100, and you're also going to use masses. Okay, so that's the solution. Now, let's look at analysis of a pure substance. So here, for analysis of a pure substance, you're trying to determine its formula. And there's two types of formulas generally. There's empirical formula, which is the simplest ratio of elements, and there's molecular formula, which is the real ratio of elements. So you need a known chemical reaction for the substance of interest. This is just like the analysis of a mixture. The substance must react completely and quantitatively, just like the analysis of a mixture. And usually you determine the empirical formula. A common practice is the determination of the formula of a hydrocarbon by combustion. So this is a hydrocarbon, hydrogen and carbon, hydrocarbon. You combust it with oxygen and you make CO2 and H2O. So here's the technique behind this. What you do is you take your substance and you pass oxygen gas through a chamber that has your substance in it, and you heat this. And when you heat it, you cause combustion. When you cause combustion, the products, because of the heat, will be CO2 gas and H2O gas. So there will be O2 coming through this chamber, pushing the CO2 gas and H2O gas through the chamber here. And so when these three gases enter this particular portion of the device, the H2O is absorbed by some magnesium perchlorate. And the CO2 and the H2O pass through. And here you have another little chamber that absorbs carbon dioxide. So we have some sodium hydroxide to do that. And the O2 passes through. So you weigh these chambers before and after, and by weighing them before and after, you will be able to get the mass of H2O by difference by measuring this chamber before and after, and you will be able to get the mass of CO2 by difference by weighing this chamber before and after. So what do we do with these masses of H2O and CO2? So here are the calculations. And here's the idea behind the calculations. You take the mass of CO2 and turn that into moles of CO2. The moles of CO2 can give you the moles of carbon in CO2. And the moles of carbon in CO2 are going to equal the moles of carbon in your substance. It's a similar process for the H2O. the mass of H2O can be used to give you the moles of H2O. The moles of H2O can give you the moles of hydrogen. And the moles of hydrogen in H2O equal the moles of hydrogen in your substance. So to do this, if we want to go from mass to moles, we're going to need molar masses of CO2 and H2O. So once you find the moles of carbon and the moles of hydrogen, normally you take the moles of hydrogen, put that on top, the moles of carbon, put that on the bottom, divide one into the number, and you get something that looks like this. And X hopefully is the number like 1 or 2 or 3 or 4. Now, if not, if X happens to be 2.5 and this happens to be a 1, what do? We double everything. So we turn the hydrogen into 5 and the carbon into 2. And that's how you get the empirical formula. So you can get the molecular formula also by combustion. And for that, you just take the molar mass of the compound, which has to be given, usually found by mass spectrometry. You take the molar mass of the compound, divide it by the molar mass of the empirical formula, and you get some factor. And you take your empirical formula and you multiply by that factor. So here, in this case, I have carbon 1 and H is some number other than 1. And here, carbon is X and H is Y. And that's how you figure out the molecular formula. So let's take a look at this in practice. So using combustion analysis, we're going to determine the empirical formula of a hydrocarbon. And using the molar mass of the compound, we're going to also figure out the molecular formula. So let's start off first with the empirical formula. So I'm trying to get the piece of paper I have underneath here so that we can do this. All right. So what we're going to do, first of all, is we're going to take the mass of CO2 and get the moles of carbon. So I'm going to put moles of carbon here, dot, dot. And we're going to start with 3.447 grams of CO2 times 1 mole of CO2 to 44.01 grams of CO2. And then I'm going to multiply by 1 mole of carbon to 1 mole of CO2. And we're going to get the moles of carbon here. And you can see that the answer is going to be less than 0.9 because 3.4 is less than a tenth of this. So a tenth would be 0.1. So maybe 0.09 for the answer, something like that. So let's find out. 3.447 divided by 44.01. And we get 0.07823. So we get 4 zig figs out of this mole of carbon. Now you might be wondering, why in the heck are we putting this in here? That doesn't seem important because the moles of carbon equal the moles of CO2. Well, here I can show you that with my calculations that I am getting indeed the moles of carbon and not just the moles of CO2. I don't have to do any convincing here. The units bear it out. Now let's do that for the moles of hydrogen. We have 1.647 grams of H2O. We're going to multiply by 1 mole of H2O per 18.02 grams of H2O. And then here we have to write down 2 moles of hydrogen to 1 mole of H2O. Because for every 1 H2O, there's 2 hydrogens. It's a 1 to 2. So 1 H2O, 2 mole of hydrogen. So you see, if we didn't do this sort of thing, we might make the mistake and get the wrong moles of hydrogen. So this is the kind of work I expect to see for a problem like this on the exam. Okay, so I'm going to kind of estimate this. This is about a tenth of that. And then, so that ends up being 0.1, if you will, a little less. And then 2 over 0.1 is going to make this, well, that's going to make that a huge number, I think. No, my bad. it's going to be 2 times a tenth, which would make it like a 0.2 or 0.15, something along those lines. Okay, so let's try this. 1.647 times 2 divided by 18.02. Now, some of you may have noticed as I do these problems, what I do is I multiply everything in the top and then I divide by everything in the bottom. And I don't do equal, equal, equal as I go along. I just put this times that, divided by that, and I get my answer. And I don't do the ones because they don't affect the answer. Okay, and I do that because it's a time saver. So I get 0.1827, and I get 4 significant figures. So I'm going to call this 80 because I get 796, so that would round this way. So a mole of hydrogen. Okay, so that's how many moles of hydrogen, that's how many moles of carbon. And I'm going to go ahead and try this with them rounded and see how it comes out. And so here's one way to do it. You take your 0.1828 moles of hydrogen over your 0.07832 moles of carbon, and you divide one into the other. Okay, so I'm going to divide this by 0.07832, and I get 2.334 mole of hydrogen to 1 mole of carbon. Now, I was hoping that would be a whole number, but it wasn't. So I need to make some sort of adjustment to make this a whole number. And that means I'm going to multiply the top and the bottom by the same amount. Now, if I double this, double the top and double the bottom, the top becomes 4.66 something, right? And 4.66 is not a whole number. And the bottom becomes 2. But I'm thinking if I multiply by 3 over 3, so I'm multiplying by 1, I should get a whole number out of this. Let's see what 3 times this number is. 3 times this number is 7.002 mole of hydrogen to 3 mole of carbon. So I think this must be the correct answer for how many carbons and how many hydrogens. So I'm going to say C3H7. And there's your answer for the empirical formula. I'm going to circle that. Now, another way to use these numbers is this way. I'm going to write carbon 0.07832, hydrogen 0.1828. So these are the ratios for the subscripts in the formula. But we don't like to write ratios that way. We like to write ratios as whole numbers. So what you do is you take this and you're going to divide each of these by the lowest. And the reason you do that is that you're going to get one number that is 1 and the other number that is not 1, but greater than 1. So here we get 2.334. And here you do the same trick. You don't want that guy to be, if you will, such a fraction or a decimal. You want it to be a whole number. So in this case, I would multiply the whole thing by 3, and it becomes C3H7. So they both work the same way. If you're going to do it this way, normally you want to put the number of hydrogens on top. Now this way comes in handy if you have more than 3 elements, because what you're going to do is you'll still divide by the smallest, and then you make your adjustments. Okay, so that's the empirical formula. Now, to get the molecular formula, whoops, I can't spell formula. What you're going to do is you're going to take the molar mass of the molecular formula divided by the molar mass of the empirical formula. And remember, this is the empirical. And the way I remember how to spell this, empirical, is I think empire, which is EMPI. So empirical, and maybe you could say it that way to help you remind you how to spell it. You call it the empirical formula. Nonetheless, this is how you spell it. Now, we were given the molar mass of the empirical formula earlier, and I believe it's in the page below here. But we're given the empirical formula is 86.2 grams per mole. And I'm going to put grams per mole here. So what is the molar mass of this? Well, 3 times 12 is 36.03 for that. I'm going to put my little work here. 7 times 1.008 is going to be 7.0. 7 times 8 is what, 56 or something like that? I don't know why, but I have a problem with 7s and 8s. So we know 7 times 7 is 49 plus another 756. This works out. So this comes out to 36 plus 7 is 43. And then 0.0, we'll call it 9. So we've got 43.09 grams per mole. And it doesn't take even a rocket scientist to figure out that that'll go into that 2 times. So that's our factor. So we take the empirical formula and you basically multiply this factor times each subscript. So we get C6H14, and that's the molecular formula. And we can double check this by checking to see if the molecular formula of this compound has that molar mass. So 6 times 12 is what? 72. 14 times 1 is 14, and we get 86, which matches that. Now notice I didn't do a great deal of work here as far as trying to get the correct number of significant figures. I just want to see if this would match what we had there, and it certainly seems to. So this is the molecular formula, and here's the empirical formula. Okay, good. Now, I have one more or two more problems here. One more problem we're going to do for the rest of this particular part of the lecture. So this will be the end of part 1 here. So how do you analyze a pure substance with carbon, hydrogen, and oxygen? And the answer is you combust it again and you get CO2 and H2O. But oxygen puts a little twist in the plot. So it does not affect what we do at first. You determine the moles of carbon and carbon dioxide. That's the moles of carbon in the substance. So that would be X for the formula CXHYOZ. You determine the moles of hydrogen, H2O, which equals the moles of hydrogen in the substance. So you get Y. So how do you get the moles of oxygen? Well, you have to do it a little tricky way. And here's what you have to do. You determine the grams of carbon in CO2, because that equals the grams of carbon in your substance. You determine the grams of hydrogen in H2O, which equals the grams of hydrogen in your substance. If you take those two masses and subtract that from the mass of your substance, you get the mass of oxygen. Okay? So the mass of oxygen, the mass of hydrogen, and the mass of carbon, add them together, has to equal the mass of the substance. Therefore, the mass of the substance or the mass of oxygen has to equal the mass of the substance minus these two. So once you get the mass of oxygen, you will determine the moles of oxygen in the substance, and that is Z. So let's take a look at an example here. Using combustion analysis to determine the empirical formula of a compound containing carbon, hydrogen, and oxygen, you have isolated an acid from clover leaves, and it contains only the elements carbon, hydrogen, and oxygen. Burning 0.513 grams of the acid in oxygen produces 5.01 grams of CO2 and 1.03 grams of H2O. What is the empirical formula? So remember, we're going to treat this just like it was a hydrocarbon, which is carbon and hydrogen at first. And the first thing I'm going to do is I'm going to calculate the moles of carbon. And that's going to be 0.501 grams of carbon times 1 mole of carbon over 40, that's CO2, CO2, 44.01 grams of CO2, and then 1 mole of carbon to 1 mole of CO2. Many students do not put this into their calculations, and it trips them up. You need to put it in there. So here we have 0.5 over 44. So this is not even going to be 1/10. It's going to be like 0.01, something like that. So let's see what we get here. 0.0, oh, clear, 0.501 divided by 44.01 is equal to, and we get 0.01138 mole of carbon. Now for the moles of hydrogen, we get 0.103 grams of H2O times 1 mole of H2O per 18.02 grams of H2O, and times 2 mole of hydrogen per 1 mole of H2O. So here I'll end up getting 0.2 over 18, which is basically close to that number, I think. Well, let's find out. 0.103 times 2 divided by 18.02. And sure enough, look at that. We get 0.1143 mole of hydrogen. So these numbers are so similar that I'm just going to take the guess that the number of carbons equals the number of hydrogens in the formula. Now we need to get the mole of carbon. Now for the mole of carbon, we have 0.501 grams of CO2 times 1 mole. Oh, I'm sorry. We need the grams of carbon. So I'm going to take this number here, 0.01138 mole of carbon, and multiply by 12.01 grams of carbon to 1 mole of carbon. Okay, and I'll do the same for the grams of hydrogen. I'll take the 0.01143 mole of hydrogen times 1.008 grams of hydrogen to 1 mole of hydrogen. So here I can see the answer is going to come out really close to 0.0114 because I'm multiplying by 1. So here I get 0.01152 grams of hydrogen. And up here I get 0.01138 times 12.01. I get 0.1366, and actually I'm going to call that 0.1367 grams of carbon. Okay, so now I'm going to take these two numbers, and I'm going to take the mass of the substance, which is 0.513 grams, and I'm going to subtract from that 0.1367 grams, and subtract from that also 0.01152 grams. And let's see what we get. And we get 0.365 grams. I'm going to go ahead and round it to where it'll probably give us the right answer. So now I'm going to take that, and remember, this is the grams of oxygen. So I'm going to take the 0.365 grams of oxygen, multiply it by 1 mole of oxygen per 16.00 grams of oxygen, and we will get our moles of oxygen. And we get 0.0228 mole of oxygen. So I'm going to take these three numbers that I'm going to circle, And I'm going to write the formula out as follows. C 0.01138, H 0.01143, and oxygen 0.0228. And what am I going to do? I'm going to divide by the smallest. We can see that carbon is going to end up being 1. Hydrogen, if we want to look at the significant figures, it ends up being 0.01143 divided by 0.01138, and we get 1.00. I'm going to go ahead and round to 3 zig figs because that's where it should be. This is exactly 1 because that divided by that is exactly 1. And for oxygen, let's see what we get, 0.0228. I can already see the writing on the wall, can't you? It'll go in 2 times. So divided by 0.01138, and we get 2.00. So our formula is CHO2, and that is the empirical formula of the acid. Now, is that the molecular formula? No. I know it's not the molecular formula, but this is the empirical formula. Okay, so you can see the steps were first to calculate the moles of carbon, then the moles of hydrogen, then the grams of carbon, then the grams of hydrogen, and then over here, the grams of oxygen, and finally, the moles of oxygen. All right, thank you for listening.